Now in this section we're going to introduce the idea of the inverse of a matrix. Now an inverse is not something that every matrix has. Only some matrices have inverses. But when they do, those inverses are quite useful. And in fact, simply just knowing whether a matrix has an inverse or not, even if you don't know what the inverse might be, just having the information of whether a matrix has an inverse or not can be quite illuminating and can give you valuable information. So before I tell you what an inverse is formally, I want to remind you of a certain phenomenon from just the ordinary real number system. So pretend you're back in high school and I gave you an equation like this: 3x is equal to 7. Well, most people would say something like the following. They'd say, okay, if you want to solve this equation, this is a linear equation in one variable, by the way, you'd multiply both sides, or you might even say divide. I divide both sides of this equation by 3. But what if I wanted to specifically word it in terms of multiplication? What you would be forced to say then is you could say, okay, well, we can still deal with that. We just need to multiply both sides of the equation by 1/3. That's the same as dividing by 3, right? So you'd end up with something like this. You'd have 1/3 times the left-hand side is equal to 1/3 times the right-hand side. And then you could take that a step further and you could say, okay, and these are the steps that you probably wouldn't even write down, but I really want to take the time to go through this carefully. What you could do now is use the associativity of real number multiplication, right? You have 1/3 and 3 and an x on the left-hand side, all being multiplied. And the brackets indicate that the 3 and the x are to be multiplied first. But you can shift the brackets and multiply the 1/3 and the 3 first, which would give you x. And then what on the right-hand side, I'll just write 7 over 3 because that's what 1/3 times 7 equals. That's not really where the interesting things are happening. It's the left-hand side where all the interesting stuff's happening. So, okay, well, what's 1/3 times 3? Well, 1/3 times 3, that's just equal to 1, right? So that's quite nice. So really what you have is just 1 times x is equal to 7/3. And multiplication by 1 doesn't change anything. So what you finally end up with here is just, and this is why multiplying by 1/3 worked to solve this equation, but you end up with x is equal to 7/3 finally. So that is something that you would do, and I've kind of squished this in here as a side note, but there was a time when that was an entire exercise. That was something you were asked to do, and that was a considered work that needed to be done, and you would solve that as a problem. Well, I just want to remind you of that now going forward to put you in that frame of mind. It would be nice if we could solve matrix equations like this. And the thing is we can actually, just not always, not all the time, right? What was important here? Well, it was important that 3 actually had a multiplicative inverse, right? And in the case of the real numbers, its multiplicative inverse is 1/3. Are there any numbers that don't have a multiplicative inverse in the real number system? And the answer is yes, but there's only one, and that is the number 0. 0 has no multiplicative inverse, and that is a number you can multiply by to turn it into 1, right? In the case of 3, if you multiply it by 1/3, that turns it into 1, and that's exactly why it was useful in this situation. So some matrices have multiplicative inverses as well, and when they do, we say that they're called invertible. Okay, and notice that I start this definition with a square matrix. Only square matrices can have inverses. Okay, so start with the assumption that you have an n by n matrix A. It's invertible if there exists what? Some other n by n matrix of the same size, which that's the matrix that we're going to say is its inverse. But what's the condition? What's the property that this matrix has to have in order for A to be invertible? Well, you've got to be able to multiply these two matrices together and get the identity back. That's the key idea, right? Just like if you multiply 3 and 1/3, you get 1. That's what makes 1/3 the multiplicative inverse of 3. So what would make this matrix B the multiplicative inverse of A, or we just use the language inverse, is if you multiply them together and you get the identity. But actually, you have to be careful here. You need to be able to multiply them in either order and get the identity, not just simply multiply them in one order. Okay, and I'm going to write IN here just to be very careful to make it specific here. But of course, that should follow obviously, right? If A is n by n, and B is n by n, and you multiply two n by n matrices, if you write out the dimension diagram, you'll see that the product is going to have to be n by n as well. So actually, this subscript of n is redundant. So I'm going to remove that. And I shouldn't say obvious. It's not obvious, but it's a direct consequence. And if you think about it the right way, you can come to that conclusion. Sometimes that's what I mean when we say the context makes the dimensions of this identity matrix clear. It doesn't mean it's always going to be clear to every person at every time, but it means if you give it some thought, you can come to that conclusion. Okay, so that's the condition that's required for B to be the inverse of A. And in fact, the symmetry of that requirement automatically implies that if A is invertible and B is the inverse of A, well, then B is also invertible and A is the inverse of B. It's a two-way street. It works both ways, right? Really what it comes down to is this. Two square matrices are inverses of each other if you can multiply them together and get the identity. That's, roughly speaking, that's what we just said. We said it with more formal language. Okay, let's look at an example. And just to get you out of the impression that A and B always have to be the letters used for matrices, I'll just go out of my way to use different letters, even though I could have used any letters for these matrices, but I've chosen to use capital F and capital G. Here's an example of two 2 by 2 matrices. Let's multiply them and see what happens. So let's multiply F and G in this fashion. So we have 3, 7, 2, 5. And we're going to multiply that by 5, -2, -7, and 3. So the product is going to also be 2 by 2 because both of the factors are 2 by 2. And what do you get if you multiply these matrices? Well, let's do the first 3 times 2, or probably 3 times 5 plus 2 times -7. That's going to be 15 minus 14. 7 times 5 plus 5 times -5. That's going to be 35 minus 35. And then if we go 3 times -2 plus 2 times 3, that's going to be -6 plus 6. And then lastly, 7 times -2 plus 5 times 3, that's going to be -14 plus 15. So you end up with, hey, that's the 2 by 2 identity matrix. Okay, so that's what we would expect if we were hoping that G was the inverse of F, or vice versa. But this is not enough to say yet that G is the inverse of F. We'd have to check that it works the other way as well. So let's multiply G and F in this fashion. So 5, -2, -7, 3. And then we have 3, 2, 7, 5. So let's multiply them in that direction. And you can check. I'll leave it to you to check this, but you can work it out and you'll find that you do actually get the exact same result. And that's not always going to work with multiplication, remember. If you change the order of factors, you can drastically change the result. There's no reason to expect in general that if you multiply two matrices that changing the order of the factors might not change the result. You should always assume that it could change the result. So in this case, we had to check them both to know for sure. But since we got the identity in both cases, now we can make or draw this conclusion. So therefore, we can say that the inverse of F, I'm going to write it out as an actual matrix just to avoid using the letters. So the inverse of that matrix, 3, 2, 7, 5, happens to be the matrix G, which is 5, -2, -7, and 3. And you can also, like I said, this works two ways. You can say that the inverse of this matrix, 5, -2, -7, and 3, is actually 3, 2, 7, 5. So F is the inverse of G, and G is the inverse of F. All right, so let's make a couple of comments, and we'll actually see where this is useful. So the first one, we've kind of already said this, but let's just say it once more for the record. If you have a matrix that's invertible, that means it has some inverse. Oh, I forgot some notation here. Let me clarify back here. There should have been an extra comment here. And right, you probably figured this out by what I did in the example, but we write that A inverse is equal to B. So in the sense of if B is the matrix that satisfies this relationship, if you multiply it by A in either direction, you end up getting the identity back. Then we say that B is the inverse of A, and we write this notation. So that it's kind of like the transpose. You write this superscript, but instead of it being interpreted as an exponent, it's just to let you know we're talking about the inverse. So you just write a -1 as a superscript. So this is how you can say that the inverse of a matrix is given by something, okay? So back to this remark, if A is invertible, then it has some inverse, which the notation we use for that inverse is like so. You'd read this aloud as just A inverse. Okay, well, it turns out that if A is invertible, then so is its inverse. A inverse is also invertible. It means it has its own inverse. But actually, the nice thing is, it is exactly what you'd probably hope for, which is that the inverse of the inverse is always the original matrix. So the inverse of A inverse is always just going to be A. So if you continually take the inverse of a matrix, you're not going to now cycle through an indefinite list of matrices. You're always going to loop back to the one you started with after 2 iterations. Okay, that's the first remark, but the second remark lets us know right away we have an immediate application of matrix inverses. Okay, so if you have an invertible matrix A, and you look at some matrix equation for which A is the coefficient matrix, you can immediately solve that equation without having to do any row operations, assuming you actually have the inverse, right? That's one thing I haven't told you yet is how do you find an inverse if a matrix has one, but we'll come back to that later. But let's say you knew that your coefficient matrix A was invertible and you had access to the inverse, you could write down the unique solution for which there would be a unique solution. That's one of the things that follows from your coefficient matrix being invertible. But that unique solution would be exactly equal to the constant column multiplied on the left by A inverse. Okay, let's look at an example of that. Okay, so here we've got a nice linear system of two equations in two variables. You can write out its matrix equation, right? Let's consider it as a matrix equation. So the coefficient matrix is going to be 3, 2, 7, 5. My variable vector is going to be x1, x2. And then my constant column is going to be 1, 4. By the way, this was chosen on purpose, but notice that this matrix is exactly the matrix F from the previous example, which means we do know that this coefficient matrix is invertible, and we know that its inverse is actually G. So what we're going to do, this is kind of like this situation, right? 3x equals 7. We've got ax equals b, where a is invertible, just like 3 was invertible. So we're going to, what do we do here? We multiply both sides of the equation by the inverse of 3. So let's do that here. We'll multiply both sides of the equation by the inverse of our coefficient matrix, which was 5, -2, -7, and 3. So that's what we're going to get on the left-hand side, but of course we also have to now do this on the right-hand side as well. So we'll have 5, -2, -7, 3, multiplied by our constant column. Notice something here. We multiplied the inverse onto both sides of the equation, but we did it on the left in both cases. So here's what I mean by that. Notice if I had done this, if I had done that, which is a common error, by the way, that would not work. In fact, this product is not even defined because the dimension diagram wouldn't work out. This is a 2 by 1, and this is a 2 by 2. So you can write out the dimension diagram. You'll see that these two matrices cannot even be multiplied in this fashion. But if I put the inverse on the left, then I know it's the same. So if you're multiplying both sides of the equation by a matrix, you have to do it on the same side of both sides of the equation. So in this case, we did it on the left. Okay, so now we can, in theory, we could now multiply these two matrices first to see what happens, or we could multiply these two matrices first. But we already know that this product is equal to the identity. So what we're going to do is just say, look, this is equal to the identity matrix 1, 0, 0, 1. And by the way, let me remind you of something. This is not work that needs to be shown, but I just want to remind you, if you multiply anything by the identity matrix, it will not be changed. You can always just check by directly multiplying it out to make sure. But if you do that, you're going to have a 2 by 2 and a 2 by 1, right? So the dimensions work out, and the result is going to be a 2 by 1. So we'll write out the space for the product and actually carry out this multiplication. You've got 1 times x1 plus 0 times x2. And then here you'll have 0 times x1 plus 1 times x2, which will give you x1, x2. So really, multiplying our variable vector by the identity matrix, because that's what this really is, it's the identity matrix, is not going to have any effect. So what you end up with here is you can essentially just strike them out and say they cancel, which is what you may often choose to do in the future, because they just cancel out and give you the identity, which when you multiply by the identity doesn't change anything, so you can essentially pretend it's not there. So you're going to be left with, in the end, just your variable vector, x1, x2. But then over here, well, this is another product to work out, right? This is a 2 by 2 multiplied by a 2 by 1. It's going to have the same dimension diagram, so the result is going to be a 2 by 1. And what do you have? You'll have 5 times 1 plus negative 2 times 4. That's going to be 5 minus 8. And then if you do the second entry, you'll have negative 7 times 1 plus 3 times 4. That's negative 7 plus 12, which is positive 5. So notice how we got the solution to this linear system without doing any row operations, without doing any substitution or anything like that. So how did, well, so is that something we can generalize? Well, you should also think about, for a moment, think about the fact that, well, where did this inverse come from? Okay, well, we knew it was the inverse of the coefficient matrix based on what we concluded in the previous example. Well, how did we know to check that matrix? Well, it was just given in the question, right? So it's not immediately clear at this point how you would find an inverse. Like if we hadn't done that example and you were just encountering this linear system, how would you know to multiply both sides of the equation by this matrix? And that's a more challenging question, and we're going to answer that in the rest of this section.